We'll be learning catalytic hydrogenation. What is catalytic hydrogenation? It is a chemical process where hydrogen gas is added to a molecule. This molecule, here it is an unsaturated compound. Okay, unsaturated compound are alkenes. Okay, alkynes. Alkenes contain double bonds, alkynes contain triple bond. So whenever hydrogen gas is added to such unsaturated compounds in the presence of metal catalyst, which will be palladium on carbon or platinum on carbon or Raney nickel, the product formed will be saturated compound where only single bonds are present. Okay. This is called as catalytic hydrogenation. Usually in catalytic hydrogenation, we will be using all these metal catalysts with high pressure of hydrogen gas and high temperature. Let us see an example. We will be taking an alkene which is 1-propene. This is 1-propene. When it undergoes catalytic hydrogenation in the presence of metal catalyst palladium on carbon, we will be getting propane. It is saturated compound. So this is called as catalytic hydrogenation. We will see the mechanism for this reaction. CH3 CH double bond CH2 plus H2. So this bond is taken by this carbon because primary carbanion is more stable than secondary carbanion. Okay. Now hydrogen will take the bond and the products will be CH3 CH plus. This carbon gets a positive charge because it is electron deficient, and the carbon here will be negatively charged, plus H minus and H plus. They have been dissociated, right? Now this H minus, it will attack the positively charged carbon, and this H plus will form bond with this negatively charged carbon, giving us propane. CH3 CH2 CH3. So here this metal catalyst, what are the metal catalysts we will be using in this catalytic hydrogenation? They will be facilitating the reaction by providing a surface where this hydrogen H2 will be dissociated as H plus and H minus, and this H plus and H minus will attack the unsaturated compound, which is 1-propene, and will give us our final product, which is a saturated compound, that is propane. So that is the use of metal catalyst in this catalytic hydrogenation. We will see another example where we will take both double bonds as well as an aldehydic group. So let us take CH2 double bond CH, CH2, CCH3, CH3, C double bond OH. This C double bond OH is an aldehydic group. Okay, it will undergo catalytic hydrogenation in the presence of Raney nickel. So what will be the product here? CH3, this will be CH3, CH2, CH2, CCH3, CH3, CH2, OH. So first in this we will be reducing the aldehydic group by using H2 molecule. Then later on we will be reducing this alkene, this double bond, to 2 single bonds, that too by using another H2 molecule. Now we will see the mechanism for this. We will see the mechanism for this reaction. Okay, CH2 double bond CH, CH2, CCH3, CH3, C double bond OH. To this we will be adding H2. Okay, oxygen has 2 lone pairs. This hydrogen will take the bond and they will be dissociated as H minus and H plus. Now this oxygen will donate one of its lone pair of electrons to this positively charged hydrogen and will form 3 bonds. Oxygen will be forming 3 bonds here. As oxygen is forming 3 bonds, it will get a positive charge on it. Okay, C double bond OH. As oxygen is forming 3 bonds, it will get a positive charge. Then it will take the bond from carbon, leaving this carbon positively charged. CH2 double bond CH, CH2 CCH3 CH3 COH, carbon gets a positive charge. Now this H minus will attack this positively charged carbon and we will get H there. We will be forming CH bond, CH3 CH3 CH2OH. Now we have to reduce this double bond. For that we will again add another H2 molecule. Again this H2 will be dissociated as H minus and H plus. Okay, here this double bond will be taken by this carbon because primary carbanion is more stable than secondary carbanion and secondary carbocation is more stable than primary carbocation. Okay, so what will be the product here? CH2 minus carbon, this carbon gets a negative charge. The second carbon gets positive charge because it is electron deficient. CH2 CCH3 CH3 CH2OH. Now this negatively charged carbon hydrogen will attack the positively charged carbon and this positively charged hydrogen will form bond with the negatively charged carbon and we will get our final product, that is CH3 CH2 CH2 CCH3 CH3 CH2OH. Okay, we will see another example where we will be taking ketone. Okay, even this one here, when it undergoes catalytic hydrogenation in the presence of ranitidine, they will be converted into alcohols. Another straight chain ketone, when this undergoes catalytic hydrogenation in the presence of metal catalyst, it will form alcohol. The same mechanism we have to follow till here, where oxygen will donate its, it will not donate, it will share its lone pair of electrons with the positively charged hydrogen. It will form 3 bonds, gets a positive charge, will take the double bond from carbon and this carbon will get a positive charge. The remaining H minus will come and attack this positively charged carbon, giving us alcohol. The same mechanism we have to follow this for these two examples. So till now we have seen that ketones, they are reduced to alcohols. Okay, in the previous two examples we have seen that ketones, when they undergo catalytic hydrogenation in the presence of a metal catalyst, they will be reduced to alcohols. But there is an exceptional case where ketones, they are first reduced to alcohols and then reduced to alkanes, which means the final product of the ketone will be alkane. So this occurs only when the ketone is present at benzylic position. The ketone group should be present at the benzylic position. What is benzylic position? Benzene ring. To this benzene ring, when we attach this group, the carbon at this position is called as benzylic carbon, and that position is called as benzylic position. So if ketone group is present at this benzylic position, only then the ketones are reduced to alkanes. So when this undergoes catalytic hydrogenation in the presence of metal catalyst palladium on carbon, the product will be ethyl benzene. Okay, this is acetophenone, which is reduced to ethyl benzene. Now we will see the mechanism for this. First we will take acetophenone, C double bond O, CH3. To this we will add H2. Now this hydrogen will take the bond and they will be dissociated as H minus and H plus. Oxygen here will share its lone pair of electrons with this positively charged hydrogen, and that oxygen will be forming 3 bonds, C double bond O hydrogen, As oxygen is forming 3 bonds, it gets a positive charge. Now this positively charged oxygen will take the bond from carbon, and this carbon will get a positive charge because it is electron deficient now. Okay. OH, this is an alcoholic group. Now this H minus will attack positively charged carbon, giving us alcohol. OH, H. This compound is an alcohol. Okay. Now what did we see here? Ketones, they are first reduced to alcohols. As this ketone group is present at benzylic position, this will be further reduced to alkanes. So for that again we have to add H2. Okay, so this H2, this will be dissociated as H minus and H plus. Now this oxygen will share its lone pair of electrons with this positively charged hydrogen, and again it will form 3 bonds. Okay, this oxygen, it will form 3 bonds, H, H, CH3, H. As oxygen is forming 3 bonds, it gets a positive charge. Now it will take the bond from carbon and will leave this molecule as H2O. Water molecule is eliminated and this carbon will get a positive charge. Okay, benzene group, CH, CH3, this carbon will be getting positive charge. Now this H minus will attack this positively charged carbon, and it will give us our final product, which is ethyl benzene. CH3, 2 hydrogens. So this can occur only when ketones are present at benzylic position. This is ethyl benzene. So this is catalytic hydrogenation.